Lecture 3 on single variable unconstrained optimization problems. The classical approach. A single variable unconstrained optimization problem is the problem of the type optimize z equal to f of x subject to x element of the closed interval ab, where a and b may be finite or infinite. Local and global optimum. A function f of x defined on the set S has a local minimum at the point x0 of S if f of x0 is less than or equal to f of x for all x in the small neighborhood of x0. That is, for all x such that the absolute distance of x from x0 is less than epsilon, where epsilon is a small positive number. The function f of x has a global minimum at the point x0 of S if f of x0 is less than or equal to f of x for all x in S. The global minimum of f is therefore the minimum of all local minimums in S. We illustrate this by this diagram. We draw the x-axis and also the y-axis. We consider this curve y equal to f of x defined on this interval from a to b. Then the local minimum points are located at the following point. Here is the first local minimum point, and the value of the function at that point is here. F of x0 is the value of the function at this point, and the small neighborhood around this point x0 is this. The second local minimum point is here, x0, and the value of the function at the point x0 is here. Then the small neighborhood around this point x0 is this. We also have local minimum point here, whose function value is at this point, f of x0, and the small neighborhood around the point x0 is this. Now, let us consider the middle local minimum point. Observe that for any point x taken within this small neighborhood, if we take the point to the left of x0, the value of the function will be here. So at that point we have f of x. If we take it to the right, we'll have the value of the function here, which is also f of x. So the point x0 is a local minimum point if f of x0 is less than or equal to f of x. As you can see here, this point is less than this point, it is also less than this point. The same thing is applicable to this other point and to this other point. So these 3 points, this and this, are all local minimum points. A function f of x defined on the set S has a local maximum point at the point x0 of S if f of x0 is greater than or equal to f of x for all x in the small neighborhood of x0. That is, for all x such that the absolute distance of x from x0 is less than epsilon, where epsilon is a small positive number. The function f of x has a global minimum at the point x0 of s if f of x0 is greater than or equal to f of x for all x in S. The global maximum of S is therefore the maximum of all local maximums in S. And we illustrate this with this diagram. This is the x-axis, and we draw the y-axis, and this is our curve y equal to f of x defined over the closed interval from a to b. Here again we can identify local maximum point. Here is one of them, that is x0. At that point the value of the function is here, f of x0, and the small neighborhood around the point x0 is this. We can also identify a local maximum point here, x0, with the value of the function f of x0 here. Then the small neighborhood around x0 at this point is this. Another local maximum that can be identified on this curve is here, and the point there is x0. The value of the function at that point is f of x0, and the small neighborhood around x0 is this. As you can see, using the middle local maximum point, you observe that for any point taken in that small neighborhood, we have f of x here. To the right we also have f of x here. Clearly you can see that the f of x, the f of x0 is greater than the f of x here, is also greater than the f of x here. So the point x0 is a local maximum point. Similarly, this is a local maximum point, and this is also a local maximum point. And clearly here the maximum of all these local maximums is this point. So we can regard this one as the global maximum point. We know that the problem may have local extremum located at 3 possible points. 1. The point x0 for which the first derivative is equal to 0. 2. The point x0 for which the first derivative does not exist. And 3. The endpoint of the interval AB. So we take them one after the other. We consider the first case, case 1. That's the case where the first derivative at the point x0 is equal to 0. If the first derivative at x0 is equal to 0 and the second derivative at x0 is less than 0, then the point x0 is a local maximum point. If the first derivative at x0 is 0 and the second derivative at x0 is greater than 0, then x0 is a local minimum point. If the first derivative at x0 is 0, the second derivative at x0 is 0, and the first non-zero derivative at x0 is an odd order derivative, then x0 is neither a local maximum point nor a local minimum point. If the first derivative at x0 is 0, the second derivative at x0 is 0, and the first non-zero derivative at x0 is positive, an even order derivative, then x0 is a local minimum point. If the first derivative at x0 is 0, the second derivative at x0 is 0, and the first non-zero derivative at x naught is negative and even order derivative, then x naught is a local maximum point. Case 2. If the first derivative at x naught does not exist, then x naught may be a local maximum point or a local minimum point or neither. These situations are illustrated below. In this first case, at this point, the first derivative does not exist at x naught. And clearly, as you can see, this point is a local maximum point. Here, f of x1 is less than f of x naught, and f of x naught is greater than f of x2. Again here, the first derivative does not exist at x naught, but this point is a local minimum point. Also observe here that f of x1 is greater than f of x naught, and f of x naught is less than f of x2. You see, in this third case, again, the first derivative does not exist at the point x naught, and x naught is not a local extremum. That is, it is neither local maximum nor local minimum point. Here, observe that f of x1 is less than f of x naught, and f of x naught is less than f of x2. Case 3. That is investigating the extremum at the endpoint of the interval. If the first derivative at the point A is greater than 0, then the point A is a local minimum point. If the first derivative at the point B is greater than 0, then the point B is a local maximum point. We illustrate this with these diagrams. This, the curve y equal to f of x defined over the interval AB. At the point A, the tangent to the curve at the point A is this straight line. Clearly, you can see this tangent, which is f prime A, is positive, and the point A there is a local minimum point. Whereas here, at the point B, the tangent to the curve at the point B is also positive. Hence, the point B is a local maximum point. If the first derivative at the point A is less than 0, then the point A is a local maximum point. And if the first derivative at the point B is also less than 0, then the point B is a local minimum point. This is a diagram illustrating this. This is a curve y equal to f of x defined over the interval AB. At the point A, the tangent to the curve at that point is this line, which has a negative slope. That is, f prime A is less than 0. Hence, that point is a local maximum point. Also here, at the point B, the tangent to the curve at that point is also negative. That's f prime B is less than 0, and clearly the point B here is a local minimum point. Example number 1. Let f of x equal to 5x minus x squared be defined over the interval x greater than or equal to 0, less than or equal to 10. Find max f of x subject to x greater than or equal to 0, less than or equal to 10. Solution. We now classify all the OPTIMUM candidates. We begin with case 1. We find the first derivative f prime x, which is equal to 5 minus 2x. That's differentiating this with respect to x. That will give us 5 minus 2x. And we set that equal to 0 to find the OPTIMUM point. So solving this equation will give us x equals to 5 all over 2. So this point is a stationary point, or what we call a OPTIMUM point. So you have to distinguish between this point, whether it is maximum point, minimum point, or neither. We use the second derivative to distinguish between them. The second derivative of this function is differentiating this with respect to x. That will give us minus 2. Since the second derivative is minus 2, which is less than 0, that means that the point x equals to 5 over 2 is a local maximum point, yielding the value of the function f of 5 over 2 equals to 25 all over 4. Let us now investigate case 2, the case where the first derivative does not exist at the OPTIMUM point. Here we observe that the first derivative exists for all points in our given interval 0 to 10. So there is no case here. Case 3, investigating the possibility of having OPTIMUM point at the end point of the intervals at the point 0 and 10. First, we recall that the first derivative of our function f of x, that's f prime x, is equal to 5 minus 2x, and at the end point here 0, f prime 0 is equal to 5, which is greater than 0. So x equal to 0 is a local minimum point. We also find f prime 10. F prime 10 will give us 5 minus 2 times 10, that's 5 minus 20. 5 minus 20 is minus 15, and this is less than 0. So x equals to 10 is also a local minimum point. Example 2. Let f of x be defined as 2 minus x minus 1 squared for x greater than or equal to 0, less than 3, and f of x equals to minus 3 plus x minus 4 all squared for x greater than or equal to 3, less than or equal to 6. Find max f of x subject to x greater than or equal to 0, less than or equal to 6. Solution. Case 1. First, consider the interval from 0 to 3. For the interval 0 to 3, f prime x is equal to minus 2x plus 2. That's differentiating this function with respect to x. That will give us minus 2x plus 2. And we set this equal to 0 to obtain x equals to 1. So we now determine whether at this point is maximum, minimum, or neither. Since the second derivative is equal to minus 2, that's differentiating this function with respect to x, will give us minus 2, and this is less than 0. That means x equals to 1 is a local maximum point, yielding f of 1 equals to 2. That's when you put x equals to 1 here. Since 1 lies in this interval, that will be 1 minus 1 is 0, 0 squared is 0, and 2 minus 0 will give us 2. Next, in the interval x greater than or equal to 3, less than or equal to 6, the first derivative with respect to x is 2x minus 8. And if we equate this to 0, that will give us x equal to 4. Since the second derivative with respect to x, differentiating this one with respect to x will give us 2, and this is greater than 0, that means x equal to 4 is a local minimum point, yielding the value of the function f of 4 equals to -3. Case 2. This is the case where the first derivative does not exist in the given interval. You know, the interval given is from 0 to 6, and we know that if we plot the graph of our function y equal to f of x, you will observe that at the point x equal to 3, the first derivative does not exist at this point, since the function is not continuous at this point x equals to 3. So from the graph we see that f prime x does not exist at x equal to 3. So what do? We have to look at the value of the function to the left of 3 and to the right of 3. So a little to the left of 3 we have 2.9. So the value of the function at that point is -1.61, and the value of the function at x equals to 3 is equal to -2, while the value of the function at the point 3.1, as you take a little to the right of 3, the value of the function is -2.19. Please note, in finding the value of the function at 2.9, we are using the first function defined over the interval from 0 to 3. You know, in the first function was defined from 0 to less than 3. So we use the first function to determine this. To determine f of 3, you use the second function, since the second function is defined from 3 inclusive to 6. And also to find the value of the function 3.1, the second function is used, and that will give us -2.19. Since f of 2.9 is greater than f of 3, you can say this is greater than -2, and -2 is greater than this, is greater than f of 3.1. This implies that x equals to 3 is not a local extremum point. Now we investigate case 3. We recall that the first derivative of our function f of x was given to be -2x plus 2 in the interval x from 0 to 3, and 2x minus 8 in the interval x greater than or equals to 3 but less than or equal to 6. So we are now investigating the first derivative at the end point. You know, we were asked to determine the maximum point in the interval from 0 to 6. So the value of our first derivative at x equal to 0 is f prime 0. So we are using this. When you put x equals to 0 here, that will give us -2 times 0, which is 0 plus 2. That will give us 2. And this is greater than 0. So that means x equals to 0 is a local minimum point. We also find the value of the first derivative at the other end point, which is 6. F prime 6 is equal to, we are using this function, that's you put 6 here, 2 times 6 is 12, 12 minus 8 is 4, and this is greater than 0. Since f prime 6 is greater than 0, that means x equal to 6 is a local maximum point.